Okay. So I talked about AdaBoost. I added a regularizer, and it smoothed things out. And we saw these. The LP boost was very brittle. It focused on very, very small areas, small number of examples. So intuitively, in each trial, it only learns about these small number of examples and never gets the big picture. It's fundamentally lost, but if you smoothen, many good things happen. And in boosting, I can show that there's a big difference between these different algorithms. Here I visualized, remember I had these curves, the upper and lower bound, when I visualized the duality. Okay, this now, eta equals infinity, corresponds to the step function curve. And then there's various choices of eta, and the larger it gets, the more smooth it gets. Right? And eta equals infinity, which is this one, corresponds to the non-smooth case. So you see it here as well, what happens to the two objectives. This is the objective in the D domain. We have two domains. In the W domain, you go the other way. If you have eta infinity, you have this curve, and then it gets smooth if you make eta small. It gets smooth. Okay? Again, for these things, these two curves meet. The primal is equal to the dual. Can't visualize it, but it's true. Is that clear? So I smoothened the objective using the entropy. Now, what I really want is an explanation to go from SVM to boosting, and I'm not quite there yet. I'll show you the kind of problems I have. Intuitively, what happens is the 1-norm margin has to be replaced by the 2-norm margin, and the relative entropy regularization by the 2-norm regularization, 2-norm squared regularization. But there's many kinds of dualities and many ways to do this, and I'm not quite sure yet what's the best way. I will probably add slides later. So there's three different dualities: minimax duality, Lagrange duality, and Fenchel duality. In general, in support vector machines, everything is sort of trivial because you have quadratic loss functions, a quadratic regularization, and derivatives of quadratics are linear, and we know how to handle linear. But now, when you take derivatives of entropies, you don't get a linear function. So in the first paper on boosting, they could basically do everything. What's the optimization problem? Slack variables, the noisy case, all these issues. They could handle the bias and so forth. In boosting, this took about 10 papers. It's just much more complicated. Slack variables I will show you next. Bias term I'm working on with Kohei Hatano. So this is a common trick to handle the inseparable case that's used in support vector machines. It's known as the new trick. So what you do is you add slack variables to each of the examples, psi n. There's a slack variable for example. And then you take the minimum. And you minimize the overall slack. Or you try to get that slack small. And in the dual domain, that corresponds to capping the distribution. And working with a cap probability simplex. So pictorially, what happens now is this. You have your examples. You have a hyperplane. Now, this point is on the wrong side, so it requires slack to put it on the right side. And that trick you can use in boosting as well, and there's not that much that changes. AdaBoost changes by having additional constraints, capping constraints, and this puts all the weight on examples with minimum soft margin now. So the margin that involves slacks is sometimes called soft margin. But then there's an overuse of term, as you will see in a moment. Now, the entropy regularized AdaBoost has the entropy regularization and capping as well. Its distribution is e to the minus eta soft margin. So there's soft here, and then this whole thing is sometimes called the soft min. So soft is overused. So different kinds of softness. This is softness from slack variables, and this is softness from entropic regularization, the kind of sigmoid function type softness that you get in logistic regression, which is, comes from entropies. Questions? So you can handle slack variables. And now I will do a little bit of an overview of all these different boosting algorithms. And so here was the slack variables. So I will go back to the original, one of the first algorithms, AdaBoost. The distribution there was simply old distribution e to the minus accuracy, this is a learning rate, of the last example over normalization. So it's some kind of an update that only involves the last hypothesis. It involves the current distribution and the last hypothesis. Whereas LP-boost involved all the past hypotheses. In some sense, it's smarter. ELP-boost as well. This update is usually motivated by doing the following thing. You look at the log partition function, which is the log of the normalization. Look here, this thing. If you take a derivative of this with respect to the w, you get that the edge of the hypothesis that you just got is 0. So what you see is that minimizing this thing has the property that it corrects the last hypothesis. It corrects the edge of the last hypothesis to be 0. And there's many ways to motivate AdaBoost. Statisticians grabbed a hold of boosting, and they work a lot in that other domain. The guys at Stanford, Hasty Tip-Shirani, they wrote papers on this. I do everything in the other domain, as you will see in a moment. OK, the good thing about these AdaBoost is it's easy to implement. It adjusts distribution so that the last hypothesis is edge 0. You see that here. And when h is in plus minus 1, then the learning rate is easy to determine. If it's in a range, then you have to do a line search. The problem is it gets only within half of the optimal hard margin, and only in the limit. So and it doesn't handle the case when you you're not separable. So the original simplest boosting algorithm, you have to fix it in various ways to handle the noisy case and so forth. But this has been done. But I want to distinguish now between boosting algorithms that only work on the last hypothesis, the update only depends on the last hypothesis, versus all past hypotheses, which we call totally corrective. So this is how I classify boosting algorithms now. AdaBoost lives over here. LB-boost lives over here. And entropy regularized LB-boost lives over here. There's other ones that live over here. Logit-boost, AdaBoost star, and then there's a corrective version of entropy regularized LB-boost. And then there's other ones. You see kind of sequences of papers to arrive at the current status, which already can handle slack variables, but cannot handle the bias yet. Total boost and soft boost. So a lot of work went into this. So here's sort of an overview of the optimization problems. I'll discuss this a little bit. Any questions? So I'll discuss, yes? No. Optimization problems a little bit. This is how I motivate AdaBoost. I motivate it in the D domain, because there it's where you find the distribution. You take a divergence, a relative entropy to the last distribution, such that the edge of the last hypothesis is 0. And you make sure that your weight sum to 1. The non-negativity constraints are handled by the relative entropy. So this is how I motivate AdaBoost. If you see it this way, it's simply the max-end principle of Kullbach and Jaynes. It goes back since 1967 or something like that. That's how you can motivate boosting. The dual objective is this log partition function type thing, which you see whenever you have entropy regularization. When you see this, you should look for entropies. When you see sum of exponentials without the log, it's an unnormalized relative entropy. Okay, so this one is normalized entropy when you see the log of a partition function. Okay, now, this algorithm only gives within half of the optimum hard margin and only in the limit. Okay, this thing is really sucking up juice. If you adjust here in AdaBoost, if you push the edges all the way down to 0, then you get cycling. You get cycling in the case if the edge of the final one is, let's say, at 0.5, and if you push the edge of your weak learner, of the last weak learner, all the way down to 0, then some other guy has to push up. Then you push that one down, and you get cycling. So if you, however, adjust the upper bound smartly with a heuristic, then you get a corrective algorithm, AdaBoost star, that that optimizes the hard margin. We have done this. So you get a very quick and dirty, and it's not much more complicated than AdaBoost. It's another 1 or 2 lines in there, and you can converge to the hard margin case. The dual looks like this. There's another little change. Everything is extremely subtle, and we have tables of these dual problems. And yes?
So the cycling means slow convergence or no convergence?
No convergence at all. You only have convergence to within half of the optimum hard margin. So you're in the separable case, and there's a paper by Shapiro and Sunche Rudin where they show that it converges to only half of the optimum hard margin in the limit.
Is there a diagnostic to realize that problem?
I think they have a case where this happens, yeah.
No, like say if I'm just using boosting, AdaBoost, is there a way to realize you're actually having this problem?
Yes. There's a case where it happens.
Now, how do you understand that it's happening?
They have a proof that it converges in the limit to half, and then they have an example where it is that way. Yeah, so they looked into this thing, and the cycling you can see very quickly. Basically, it picks past hypotheses, pushes them down, something else pops up, the edge pops up. It has to pop up because if the value is larger than 0, then you have to get into this cycling, and there's no way to fix it. Whereas if you adjust this heuristic, then it works. You converge. It's just a minor little subtle thing. So if you like corrective boosting algorithms that are extremely fast to implement, then I would implement this one, AdaBoost star. Yeah.
So is this the same thing as the connection between maximum log likelihood and maximum entropy?
Maximum log likelihood and maximum?
Entropy. There were these papers by Shapir and one of his students, Miroslav Dudek, where they looked at the duality relations between maximum log likelihood and maximum entropy.
Yes. Yes. They also later on figured out this connection, yes. So I always motivated over here because it goes back to Kullbach and Jaynes. And that sort of was my big insight. We did it first together with Kivinen, and then Lafferty also had a paper on this. For me, this is more intuitive, and I got a lot of leverage by switching to the other domain. There's a lot of people who talk about, what is this, and they try to understand this thing in terms of what it means, and then they forget the log. All kinds of things happens, screwy things that people do. Here's a totally corrective version where you have a cap on the edge, and you adjust that with a heuristic. It's a totally corrective version. And then here's the relative entropy, the entropy regularized LP boost, where you do a pure trade-off. We had this for a while, but we really wanted the machine learning type thing. We wanted the trade-off. So we worked really hard, and eventually we fixed the proofs. The reason why this took so long is we proved iteration bounds for these algorithms. OK, good. You see the duals. Hopefully, we got them all right. OK. So there's also a corrective version of ERLP boost, which trades off a relative entropy, and then there's sort of a past combined weak edge. It's by Singer and guys and students. So the picture is as this. You have AdaBoost, LogitBoost, AdaBoost star. These are corrective, and these are totally corrective. Now, what are the bounds that you know? They essentially log n over epsilon squared. The nu is from the capping. So you get within epsilon. You get in within epsilon of the value of the game or within epsilon of the guarantee, log n over epsilon squared. Now this bound drove the boosting research. Quite interesting sociologically how boosting happened. I will talk about this in a moment. OK? And these only work for the hard margin case. These work for the soft margin case, with slack variables, you see. These work for the hard margin case. And then this one here, they only designed to get consistency. So if your weak learner returns something with guarantee bigger than 0, then after this many iterations, you get consistency. So we got smarter and smarter. Initially, we only were interested in consistency. Then we wanted hard margins. And then we wanted soft margins. OK? Bias we don't have yet. Complicated. Now, will this be infinitely complicated? No. The two main families are additive and multiplicative. Once you have this one worked out, you have gone a long way. OK? So now, what did I want to do next? Are there any questions at this point? So again, the key thing is I do the classical things that you do in machine learning. I motivate my problems in terms of trade-offs between a regularizer and an objective. Right? This happens to be a very screwy objective. But if you smoothen it nicely, you're fine. Now, you can go further. So essentially, machine learning has many, many messages. You should never work with this kind of a thing. Avoid this like pest. Right? You should smoothen. Everything should be smoothed and regularized. Here, I regularize. But I can do another thing. I could smoothen this. I could replace this by a soft max. And in the optimization literature, this has been done already. And I haven't developed these algorithms yet. The boosting algorithm would then be the following thing. It would be a relative entropy, and a log partition function would replace that max. It would be a soft max. And in the dual, it would be a relative entropy on the dual parameter and a log partition function again. So it's a nice symmetric thing, but that one I haven't analyzed yet. Again, what we are after in this context is good iteration bounds. So in support vector machines, they got away with publishing these papers which just give the algorithms and talk about how they work. We didn't do that in boosting. In boosting, we set ourselves more stringent goals. We actually proved these kind of bounds. Okay? Because we came from the online learning literature, the boosting comes from the online learning literature, and everything there was always with regret bounds, and we always were used to proving bounds. And it also came out of a different community, a theoretical community, the code community, and they are used to proving bounds. So this became our major design criteria. Boosting algorithms are good if you have at least a basic bound. Now, LP boost, hopelessly lost. Okay? So I spent a lot of time on this because a lot of people like sparsity and so forth. So I wanted to know, in this case of boosting, which I had studied quite a bit, what does sparsity really work? LP boost, totally sparse. You saw the example. You saw the example run. It produces sparse hypotheses, but I can fool it. And here's the example. So it's a particular constructed thing. There's a bunch of ones in there, and then there's 0.98. That means sort of 1 minus 2 epsilon. This is 1 minus 3 epsilon. This is 1 minus 5 epsilon. It's carefully constructed. It's complicated. But the effect of it, I only show it in this small table, but you can do it for any size. But what it shows is, you see, what happens here, here I wrote down the edges. The largest edge here was this guy. Yes, these are negative, and this is the largest edge. So the strong oracle will give you this hypothesis. When you add it, this is the situation. This is in there, and now the edges become this. Now the strong oracle will give you this hypothesis. See, this is here the classical way of boosting. These guys are already in. The grayed ones are not in yet. They're not in the they're not pulled into the pool yet. So these are grayed out. The oracle scans these remaining guys and picks the one of highest edge and includes it. So now I wrote down what the edges are. These are active. The minimax is minus 0.98, and here's the max, or the min. I think which one is the min? Forget it. This is the min, and this is the max. Yeah. So now you add this guy in. The value goes only down very slowly. So this is essentially minus 1, still minus 1, still minus 1. Now here's this situation. The minimum of this the value of the game is minus 0.96, which is the maximum of this and the minimum of this, I think. Yeah. Right? And now you look at the remaining edges. There's still one guy. So this is a very devious construction. Very devious construction, and it goes down, and in the last step, it's done. So I can construct this kind of thing for any size, and I essentially can show that you require omega n. If n is the number of examples, you require n over 2 iterations. LP boost requires n over 2 iterations to get within half of error half, or something like that. So it's hopelessly lost. Essentially, it's the value of the game that it produces. I should do, here's minus 1, minus 1. It stays down here, and then it jumps up. So it doesn't learn, it doesn't learn, it doesn't learn, and basically runs out of things and has tried everything, and then it learns. So this is the example, the paradigmic example, where LP-boost, the sparse problem, the sparseness totally hurts you. So from my point of view, within boosting context, we put, with these kind of examples, we put this question of using sparse things and not using a regularizer totally to rest. Okay? It doesn't work in this context. Okay, I'm seeing there's a lot of interest, so I'll discuss how we in online learning are dealing with the sparsity thing. I'll discuss this on the fly later. Okay, now, once you're done at the end, right, when you have a fixed set of weak learners, the question, how should you predict? Should you then use a sparse solution? And I have some evidence that even then it is not smart to predict with a sparse solution. And this is kind of puzzling. This was done with a student, Karen Gloscher. Essentially, LP-boost and anything that does L1 regularization is extremely brittle. Again, when you go along boosting, you put very few weights on very few examples. You only learn about these areas. You don't generalize. You don't get the big picture. You're totally lost. Okay? But even if I give you, I'm in this context where I already have given you, let's use this picture. I have given you the full picture. I've given you all weak learners. Now just ask now, combine them. What's the best combination? Well, again, a rational thing might be to predict with a solution that realizes the minimax value. Not smart. Not smart. Even then, when I see all these examples, when I have the full payoff matrix ahead of time, when I have all the weak learners available to me, I should not use the LP-boost objective. I shouldn't just predict with the optimum value. I should pull back and regularize. And these examples are very important. And if you are interested in this, you should study them. You would have to look up Karen Gloscher's thesis and continue from that. You can contact me. I bet there are examples in all kinds of contexts where you can construct worst-case examples where you learn something. At the end, I give you even everything you want. And now you have a choice to predict with a sparse solution or not. And the sparse solution is unstable. In this context, what happened is, so you have some kind of a trade-off matrix. And now you predict with the L1 objective. And I can show that by adding just one bad hypothesis, all the labels flip. So it's extremely unstable. Or by adding one bad example, all the labels flip. So it's an extremely intuitively unstable thing. And that's why I don't like it. So here's the situation. LP-boost, in this context, or the linear programming criteria, would produce a certain solution. I didn't have that last example. Now I add one more example. Now watch here. All these guys are classified as being positive, bigger than 0. That's the classification of the final hypothesis. The margin is bigger than 0. And now you add one more example, and all the labels flip. This is the kind of thing you get when you have sparsity. Okay? When you do LP-boost type. Notice it's very sparse. Do you see? The solution it predicts with is extremely sparse. Only 3 non-zeros. Now all of these scale up. I showed you just for dimension 8. One more example, and you're going to get screwed up when you put all the weight on this one. I mean, you can fool these things And please, if you don't trust me, then go home and invent these kind of examples yourself. They're not very complicated. Okay? Now, there's one context, though, where sparse solutions are useful, maybe, and that is the context if your matrix somehow is produced by a highly random process. There's a lot of randomness everywhere. Then the sparse solution has still a lot of randomness, and therefore, because it has a lot of randomness, a lot of implicit smoothing, and then you're fine. Okay? But if you construct you can always construct worst-case example where these sparse things get fooled. So that's why it's confusing. People who like sparsity publish on data that is random, and they say, oh, it works really well. And then people who argue against, they say, no, there's these counterexamples. So you have to specify your problem. If you have a lot of noise in your data, a lot of randomness in your data, sometimes you can regularize by taking your thing and modifying this thing by adding noise. Okay? That's a form of regularization. Okay, so it's very important. Also, early stopping of learning algorithms is often a regularization. Yeah? So when they compare these things and say certain things work, certain things don't work, you need to really say what are the underlying optimization problems, what did you optimize, to what precision. Because if they do sloppy computation, they have an implicit regularization. But if you do things, you see, what happens is if you have one of those LP-boost type algorithms, an L1 type algorithm, there's something counterintuitive going on. If you calculate according to very high precision, it might hurt the algorithm. So you always, when you want to report results for these kind of things, you need to specify to what precision you calculated things. Otherwise, you have implicit regularization, and your results are going to be incomparable. Questions? I'm trying a lot of opinionated things to hope that there will be a discussion, but so far, go ahead. I like discussion. Yes?
So basically, when you say that there's a lot of noise in your data, you prefer L1?
Then it might work. Then it might work. If there's a lot of L1, if there's a lot of noise in the data, then you might get away with L1 regularization. What? Because the noise is a form of regularization. Or imagine you do some kind of bagging type thing, right? You draw a subsample of a large batch. You do a sparse solution, subsample again, sparse solution, and then you average them. Of course, that's non-sparse, but you see what I'm saying? So those are all forms of smoothing and regularization. But you need something. Either you have noise in the data, subsamples, something, or you have an explicit regularization that you introduce. You have to have something. Just sparsity by itself, I don't believe it. Yes? You don't generalize. You do optimization really well. See, this is a big difference between the optimization literature and the machine learning literature. Optimization wants you to solve certain optimization problems, like linear programming. We don't care about the solution for the linear. We want to generalize well. We want to generalize on the unseen data. So optimization is always only half of the story for us, for machine learners. We need to know how to regularize so we generalize well. And that's looking towards the future. It's not looking at your fixed batch of data and just finding a solution. That's not the point. That's useless. We want to generalize. And that's why machine learning is so interesting, because we're interested in the future data. Fundamentally different thing.
So, but in areas like compressed sensing and stuff, isn't it an assumption that the data was generated by a sparse vector or something like that?
Ah, so good. I will discuss that in the end. Okay, how we handle sparsity in online learning. We did handle sparsity in a certain way, but not by picking sparse hypotheses on the way. Very important. We pin dense hypotheses on the way. We only use sparsity as a comparator. And for that, I have results. Yes?
So basically, I mean, from a statistician's perspective,
yes.
there is correlation
No. No. Okay, so if your comparator is sparse, I will talk about this at the end. Let me go through my slides, and I will talk about at the end how we, in the paradigmic example, which was the first online learning algorithm for learning disjunctions, how Nick Littlestone avoided this. Okay, I will discuss this problem. What happens is, in an upshot, and then I go through my slides, and then I'll discuss it in detail on the board. If you are in a situation where your target, or you one you compare against, the one you measure regret against, we are in the worst case setting usually in online learning. If that happens to be sparse, then you can design an algorithm that has the property that it has a small regret. It is good. It has small amount of loss. It generalizes well. Okay? However, it doesn't produce a sparse solution. It only has a good bound. So not do we, as we go along, we don't predict with sparse things in the online setting. At the end, we don't produce with something sparse. And yet we have good bounds if the comparator is sparse. So that's my answer to this. You want to, even if the comparator is sparse, the one you're shooting for, your target is sparse, you do not want to go on and produce something sparse, because actually you want to maintain uncertainty over sparse things, because you don't know which one the sparse one is right. So uncertainty over sparse is non-sparse. So you want to be highly non-sparse as you go through, learn, and you want to prove a bound that is good when the comparator is sparse. That's how we resolve this issue. Okay. Yes?
Is sparsity in the D domain equivalent to sparsity in the W domain?
Some other question. Easier questions. I don't know.
Is already sparse in some ways if you have an infinite number of weak learners that you're selecting from.
Yeah. It gets very confusing. I don't know. I don't have any smart answer to that. It's sophisticated. Somewhat it is related. I mean, in particular in linear problem, right? If the rank, the rank modulates things, right? On one thing you have rank many things, and the other thing with Caradere-Dory's thing you only need rank many things. So yes, there is some relationship, but I don't have anything more sophisticated than that. It's a good question. Sorry. Okay, so the synopsis is that AdaBoost is often unstable, right? For safety, add relative entropy regularization. The corrective algorithms, they are easy to code. AdaBoost is the easiest, but it doesn't maximize the hard margin. But with a little bit more effort, you can maximize the hard margin and so forth, and get corrective algorithms that do basically everything in terms of the bounds. In practice, the totally corrective ones are much better. They have smaller number of iterations. Sometimes they are faster overall time when epsilon is small. It's kind of paradoxical. You sort of you spend more time per iteration, but overall you're fine. And then in practice, weak versus strong oracle makes a big difference, but theoretically it doesn't. So the theory is very weak, unfortunately. So now about this bound. This was the bound why boosting came about. Rob Shapiri, in his first recursive construction, he showed this bound. After this many iterations, you have consistency.
Before that, can I ask you a question regarding the weak and the strong?
Yes. Go ahead.
So basically you're saying that theoretically there is no difference, but practically big one is better?
We have no theoretical bounds that bring out a difference between the two things, yes. But in practice, it performs better, of course, yeah.
So basically, strong, is there any intuition why? Like any?
It's the theoretical bounds are weak. The tools are weak. You know, in general, if you are in a field where you can get it just away with publishing algorithms and pretty pictures, you're doing very well. In the code community, they want to see bounds. It's pretty tough. Upper bounds are usually easier. Lower bounds are extremely hard. Like it goes up by a factor of 10, the difficulty for lower bounds. It's well known in the Stock and Fox community. Lower bounds are extremely hard. Very unthankful, but interesting. Okay, so this iteration bound became the design tool because for some reason, or for some lucky reason, Rob Shapiro, in the first construction, he actually proved the bound. He was a theoretician. And then all the later ones try to always preserve the bound. But this bound actually is rather weak. It looks good because it has log n in it. N is the number of examples. But the epsilon squared, it's kind of, you know, look here. I play around with it. If you take the trivial bound would be n, right? Dimension many weak hypotheses, because then you have n many things, and it's by Caradere-Dori theorem, any convex combination of hypotheses can always be written as a smaller convex combination of size n plus 1 because of the dimension. So n is sort of a trivial lower bound, but when you take epsilon to be 0.01, the crossover happens at 10 to the 5. And here 10 to the 7. So in other words, this bound often is better than the fancy bound. Okay, welcome to the theory and practice. Nevertheless, it was extremely useful tool. Extremely useful tool. Okay. Now here's the lower bounds that are known. I will talk about lower bounds in my last lecture on boosting a little bit. So the lower bounds that were known are these. Log n over g squared, if you have a weak oracle with guarantee g bigger than 0, to achieve consistency. He proved that lower bound. Now, that's sort of only for achieving consistency. In the more modern way, you would want to get close to the optimum hard margin. Omega 1 over epsilon squared is rather easy to prove. He uses a Hadamard matrix. Hadamard matrix is a very powerful tool for constructing hard examples. Now, if you do random matrices, you can actually prove the additional factor of log n, which matches what's in the upper bounds. But it requires that the number of hypotheses is less than roughly square root of log n. So it's further restrictions. Okay? These bounds are very hard. Klein and Young did some work on this, and Nemrovsky, very tricky proofs. If you try to read these papers, it'll take you a couple of weeks to understand them. At least it took us that long. Okay. Some conclusions for today. Adding relative entropy regularization to LP boost leads to good boosting algorithms. And boosting can then be seen as an instantiation of the max and min relative entropy principle. Those go back to a long time, 50s actually. Okay? And the relative entropy regularization is sort of the natural way to smoothen one norm regularization. Actually, relative entropy is strongly convex with respect to the one norm. So those fit together. Okay. Now, I mentioned that the 1 over epsilon squared is very bad, but it seems like if you have one-sided error means you're perfect when the example is positive, and you only have error when the examples are negative, or vice versa. Yeah? Only false positive or only false negative. In this context, this many iterations suffice, but we don't know how to prove this kind of a thing for ERLP boost. We only know how to prove this kind of a rate in very, very special cases. Okay? I'd like to show that actually ERLP boost has that property. Essentially, entropy regularization exploits one-sidedness in some magical way. Very tricky goal, but I don't know how to do it yet. Now, next time I talk a little bit about, I showed you relative entropy regularization, but I didn't show you how you found the minimum. You need optimizers. Now, when you take an optimizer off the shelf, what does it do? Gradient descent, Newton's method, gradient descent, Newton's method, all 2 norm squared regularization. So on the one hand, we spend all this time doing relative entropy regularization, but then when we want to use packages that are available to us, we're still in the old family. In other words, the packages that are around all live within the geometric family. So we made a lot of progress, but we still haven't lifted all the classical packages, whatever they are called, LBRM or whatever, all of these packages that Vichy talks about a lot. I learned a lot of them from him. They all are still in the old world of Euclidean distance squared regularization. It takes time. Once they're lifted, I think there will be a major advantage for certain problems. There's incomparability, right? Good. I do not really want to be known as somebody who sells multiplicative updates. Not true. It depends on the problem. Okay? But there's incomparable situations. Okay? So this is the open problem. So replace geometric optimizers by the entropic ones. And then there is a version of boosting algorithms where you boost and you learn, and if you cannot quite get some examples, you forget about them and focus on other things. They are more combinatorial based, they're more sophisticated, beautiful work of Jahr Freund's. And it's a little bit unfair to him that I don't review this stuff, but it's so different from what I'm doing. I basically wanted to, my goal was to show the relationship to optimization and support vector machines and emphasize that part. I could have given a totally different tutorial on boosting which emphasized that other stuff, but it's not enough time. Okay, good. So now I want to show you in a very simple context how, should I do it there? So let's do the modern way, huh? Okay. So select. Oh, good. Okay, so I explained to you, it's kind of an instructive example. The instructive example is learning disjunctions. And this is this is, goes back to Littlestone. He was one of my students. You know, Einstein means one stone. You know, and I had a student, Littlestone. It's kind of a joke. Anyway, so so Littlestone, he did the following kind of thing. But you want to learn disjunctions, right? So you get bit patterns, and let's say this is a 1. And then you get another bit pattern, and this is a 0. Okay? And then you get another bit pattern, 1, 1, 0, 1. I didn't prepare this. This is a 1. So there should be a disjunction that is consistent. Is there one literal that is consistent? Yeah, there's still one literal consistent. Make this a 0. There's no single literal consistent, right, with both 1s. 1, 0, 1. But if you took this, no. So, OK, let's do it the other way around. OK, I draw a bunch of guys down. Let's say the disjunction I'm after is this one here. That's the hidden disjunction. So the result would be 1 here, 0 here, 1, 1. OK? So you understand what I mean? You have bit patterns and a disjunction that is consistent. Right? The OR of these, let's say the monotone disjunction, the OR of this is this label. This is sort of the instances, and this is the labels. Okay, so now you do the following online game. The online game is you have a trial T. Yeah? You get a trial T. Now, you go ahead and you get an instance, xt, which is this vector here. You have to predict 0 or 1. 0 or 1. And then you get, let's call this one y hat. And then t. And then you get feedback. Feedback. yt. And then you're punished whether if they are not equal, you call it a mistake. Okay? So the goal is you do this online prediction and you want to make a small number of mistakes. So if there is a consistent disjunction, if there exists k-literal disjunction, then you get an algorithm that makes essentially less than or equal to k log n mistakes. That's what a certain algorithm does, and I will sketch you the properties of this algorithm. It's called the Winnow algorithm. Okay. So why is this related to sparsity? Imagine n is huge. So here's your n. N was this huge. The bit vectors are very wide, right? Lots of bits. And there's a small number of literals that are very important. Their disjunction explain the labels. If you give me examples where there exists a consistent disjunction, then this Winnow algorithm makes at most k log n mistakes. So it handles sparsity in a very efficient way. The number of bits to describe even what these k positions are is exactly k log n. Okay, that's just intuitively. You can prove that you cannot do any better using a VC dimension argument. Now, the interesting thing about this Winnow algorithm, it's loggerheads with all your normal machine learning literature on sparsity. Why? It's not a sparse solution. So the comparator is sparse if the target happens to be a small literal disjunction, then you get a good mistake bound. Okay, you can even view it in terms of regret. It has small loss compared to the best disjunction chosen in hindsight that's consistent with the data. Okay? So it has small amount of mistakes if the target is sparse, if there is a sparse solution. However, its hypothesis is of the following type. It's a linear threshold function. The prediction on x, the prediction on x is going to be something like w dot x bigger than a threshold. It's a linear threshold function. That's what it predicts with. It doesn't predict with a disjunction. It predicts with a linear threshold function. The point is that this thing is non-sparse. You can be motivated using a relative entropy regularization. It is a version of a multiplicative update, an unnormalized multiplicative update, but it's non-sparse. So my answer to this whole sparsity thing is as follows. Even if your target is sparse, if you know there exists a consistent thing that is sparse, in my experience, you usually do not want to predict with a sparse solution as you learn online. You want to hedge your bets and predict sort of with mixtures of sparse things. That, again, is non-sparse. But most of all, you succeeded. You have a very modest goal. You succeed if your loss is small, if the comparator is sparse, if there's a sparse disjunction. So that's how we handle sparsity. Now, in the case of disjunctions, to find a sparse solution is actually NP-complete. But you can get a good approximation. So you're working on hard problems, but a machine learning algorithm should, as it learns, it should always hedge its bets, and even if the solution is sparse, maintain uncertainty over sparse solutions, which are unsparse. In boosting, as you learn, your distribution of the example should not be sparse, it should be smoothened out. Otherwise, you get a very brittle algorithm. That's why you add relative entropy. You spread things out, you maintain sort of uncertainty over all the examples, uncertainty, but yet you prove a bound. That works well. Okay, any other questions? So I will talk a little bit about our experiments in the next class, and then I talk about multiplicative versus additive updates in the context of biology in terms of how evolution works and about why you all around and all of that kind of thing, you know. So we'll have a lot of fun. Okay, thank you.